Hello, everyone. My name is Simon Lallemand, and I work at BlaBlaCar as a system engineer. I've been working there for 3 years now, and today I'd like to give you a feedback on our big shift to containers. So first, I will start with some facts and figures about BlaBlaCar and about our infrastructure, and a bit of history of what was before. Then I'd like to present you some key principles, the principles that led this transformation at BlaBlaCar. And I will finish with a big overview of our infrastructure and go a bit into details into the tools that we have to manage this infrastructure. So first, BlaBlaCar, I think most of you know about it. So just a reminder, we're doing long-distance carpooling with a community of 40 million members. What you might not know is that we were founded in 2006, so now we have our share of legacy also in the infrastructure. And we're present in 22 countries, so that's another challenge because we have countries as far as Russia or Brazil. About the infrastructure, we started with very small in 2006 with simple web hosting, then some dedicated servers. And at some point, while the cloud wasn't really ready at that time, so we decided to go to barometer servers, so buying one rack in a data center. Up to now, in 2016, we're at 17 racks in 3 data centers. And we have even a new data center now in Moscow with 2 racks. So now we're running about 300 barometer servers, and for that we're building about 400 container images for a total of more than 4,000 containers running. About the tech evolution at BlaBlaCar, while the major changes were probably in 2012 the virtualization, even if it did concern only a small part of the infrastructure. Then we started having configuration management with Chef in 2013. Foreman for automating the installation of servers in 2014. And in 2015, we started industrializing the way we deal with hardware, and we're also starting doing containers. So there was clearly a shift in 2015. So to give you more information about why we did this, I'd like to give you the principles that were leading that shift that we made. First, we wanted to make the metal invisible, meaning that we are spending too much time dealing with the servers. At that time, we had something like 8 racks, and when we needed a new service or when the service needed to scale, we needed to buy new servers to install them one by one. That would take weeks, so it wasn't really a good solution. We could have went to the cloud at that time, but the problem that when you're building an application only on bare metal servers, it's not really fit to switch by snapping your fingers directly to the cloud. So we decided to stick to the bare metal, but to buy only 2 or 3 models of servers. Right now we have only 2. To buy 1 rack at a time, so that we can give the job of racking the servers, cabling, etc. To someone else, and the engineers don't need to go to the data center anymore. So when you are having only a few models of servers, really the idea is to change of paradigm, where we want to adapt the workloads to servers and not to adapt servers to workloads. And well, after that, we are thinking that well, if we can make this work, well, maybe later we could go to the cloud or something, but well, we'll have to check if it's cheaper. Then the other principle was concerning the network. We wanted something simple and something that would scale. That means we don't want anymore layer 2 on the whole data center. We wanted to route to the racks, meaning that the top of the rack switch is also a router. And another very big change, if you consider container solutions at that time, that we don't want NAT. We want one IP per pod, and we don't want to do NAT at the host level, but we don't want either to do NAT at the data center level, meaning that our servers don't have access to internet. Instead, we use proxies. So that allows us to really identify which service needs an internet access, who is talking to who, so that also makes better security. And the third principle is to remove snowflakes. That's another way of saying that we want cattle, not pets. Really, the big point here we want to tackle is that we want to be able to reboot any instance at any time of any service. Or we want everything being able to fail, the hardware, the service, the host, everything, but still being able to serve BlaBlaCar without any problem. And actually, a little anecdote on this. We had an unexpected help from our hardware manufacturer. And they provided us with a really interesting firmware that was doing a kind of chaos monkey. So every once in a while, servers would reboot randomly. So they didn't tell us, of course, before. And well, when you think on it, it's really a pain to seeing your servers reboot completely randomly. But it was really interesting that instead of just focusing on finding the problem, we're also focusing on how can we make things more reliable in the meantime, because we can't just hope that we'll fix very quickly the issue. So it really helped us to build resilience in the whole infrastructure. And eventually, we found out that it was the firmware which was causing those reboots. And the hardware manufacturer provided us with another firmware which fixed everything. And all of this is also changes the way of considering your servers and the service that run on it. Instead of being host-centric, we want to be more service-oriented, meaning that we want service discovery. When an instance of a service pops up, we want it to report itself automatically so the other services can join it immediately. And we also want service-based monitoring, meaning that if we lose only one instance of a service, we don't want to be alerted. We just care about the whole service. So we want to be alerted only if we lost completely the service, or if the service is endangered because there are too few instances running for it. So now, following those principles, I present you the new infrastructure ecosystem that we've made at BlaBlaCar. So first, no surprise here, containers. Otherwise, I think I wouldn't be here. So that's our answer to the hardware abstraction. Since we are having the same hardware everywhere, and we want to make it invisible, remember? So we need an abstraction layer between the hardware and what's running on it. We could have gone for the virtualization, because we already had virtualization, but it was very small at BlaBlaCar, so we'd have to rethink it from the beginning. So it wasn't the best choice for us at that moment, because containers were taking off, and it was a much better approach, we thought. So we started experimenting with containers in early 2015, and by the end of 2015, 80% of the production was migrated to containers. Then to run those containers, I thought that maybe we don't need the distribution that we had till then. So we started looking at the other distributions, and there was CoreOS Container Linux, which seemed much more easier to maintain and to install, and was made to run containers, and that's what we wanted, because we didn't want to do containers only for a part of our infrastructure, because otherwise we would have one side the legacy part running the old stuff, and on the other part the new shiny thing with containers. I think that's a bad approach. We are a relatively small company, relatively small team, so we have to focus all our effort in one direction, and we decided to go all in on containers. And CoreOS was also a really good way to enforce this, because you can't run anything else than containers on CoreOS. So that was the perfect OS for that. And it's also been very stable for us. A small anecdote about that. I recently found a VM that was running CoreOS, and that was installed. I had installed in early 2015 for some tests and running some containers. And my surprise was when I logged into this VM 2 weeks ago, it was running CoreOS Alpha in the latest version, because it had updated itself, and the containers were still there. They had survived and rebooted after each update. So it was pretty amazing to see that even CoreOS Alpha had lasted such a long time. And then we chose to use Rocket as our production runtime for containers, for everything, including stateful services. And when I say everything, meaning the MariaDB, Cassandra, and the databases that we have at BlaBlaCar. And I think we're one of the biggest Rocket deployments in production. So why we chose Rocket? Mainly because from the beginning it was designed for production. There's no demand. It's systemd based. It's the code is pretty easy to understand. They don't try to do too many things. They do one thing and they do it right. It's really modular. For instance, they have a CNI for the network, container network interface. They have customizable stage 1, meaning that they can run containers using systemd in spawn, but they can also run VMs using a stage 1 KVM or a basic CH root. We even have a customized stage 1 for our tool that builds container images. So it's really modular for that, and we like it. It also supports pods, and that's something that we wanted, because we like the idea of having only one process per container, but at some point you want to have several processes in the same context, so supporting pod is also a good thing. And a few things like having a pre-start to doing some stuff before running the main process, or dealing with dependency in the images. Basically, it supports all the features that you could expect from a container runtime, and it even supports Docker images. The cons of these solutions are, well, there are no tools for the devs, so we had to make our own tooling. And it's a bit more difficult to make it adopted by the developers, because well, we don't have the same power as the marketing from other solutions. And it's also less integrated with other actors. Like, for instance, the integration in Kubernetes is not as good as you could expect. About the tools that we make, when we started doing containers, well, there weren't many tools to do basically anything. And we didn't want to lose the flexibility that we had with configuration management and tools like Chef. So basically what we've done was to create a task force within the architecture team at BlaBlaCar to create a workflow and to decide how we could work with with all this new ecosystem, how could we build the ecosystem? And we did workshops with the whole team to validate, well, is it working okay for you guys? How do we build? We decided to build containers with this, and this. What do you think? And we were doing well, some workshops to validate all this. Well, the first time it was really not good. We're doing bash scripts, etc. We're doing some chef in containers. Well, tons of bad ideas. A lot of iterations later, where we decided to go for our own tools. And for instance, to build container images, we created Digger. So it's a container build and runtime tool. And the criteria that we had in mind while building this tool were that we wanted a quick build. We don't want it to last forever. Like the first iteration when we were using Chef to build container images, it was really too long to build an image. So that's why we didn't keep this solution. But more important, we wanted one way of doing things, because what we were seeing at that time was many people doing containers images, but each time in a different way, even sometimes in the same company, people would build the container images in different ways. So we wanted really one way of doing things, something, well, if possible, easy to understand for newcomers, something that would take care of all the templating of the configuration files, because we wanted to use the same container image in different contexts. And we wanted a good integration with Rocket. So we made the Digger, which is based on the AppSys spec also, because we wanted to use directly the image from Rocket instead of using Docker images. For a simple reason is that the format is really easy to understand. It's a simple tar file. So here you have the build directory of an image. So you have the standardized structure, and you can see that it's really inspired by configuration management. You will find the attributes, run level, where you have the scripts, and all the templates. Then we have in a manifest, we have a simple format in YAML, and we only have to define the minimal things. For instance, if I want to do a Redis image, I just give the name of the image and what process I want to run. We can also use dependencies. Like here, if I don't want a Redis image with the whole distribution in it, and let's say that I want the Debian package, well, I will put Debian as a dependency, and that way I won't have the Debian files in the image. Then on the build part, so we have different run levels. One is the build run level, and the build run level contains all the scripts that are executed from inside the container with all the dependencies. So, for instance, in the case of our Redis container, we just have a file in the build run level saying apt-get install Redis server, and I consider that I already have Debian because it's in my dependencies. And I don't even have to update or to clean after, because it's also done in other run levels in the Debian image. So I will inherit from all the apt-get update and all the cleaning afterwards. Then I have another run level, which is called builder, and which is slightly different, because in that case I will build from outside of the container. So here I have an example with a Go application. That's a BlaBlaCar application for doing Redis clusters with elections using Zookeeper, which is called Redis Dictator. So here we have a builder, and the dependencies of the builder will be Go and Git. And so in the scripts of the builder, I will just git clone Redis dictators repository, go build the application, and then copy the binary into the root file system of the container image. And in the end, in the image, I will have only the binary for Redis dictator, but not the whole build environment with Go and etc. Another thing that we can do for distributions that have a package manager which allows to install in another target for which has another target for installation, for instance Gentoo, is that we can use Gentoo stage 4 for dependencies, for builder dependencies, and then just emerge Redis server, and the target will be the rootfs of the target image, and in the image I will have only Redis server and its dependency, but not a whole distribution. Then Digger also takes care of all the templating. So basically the idea here is to have the templates and all the default attributes stored in the image, but not rendered at the build time. Instead, we're doing the rendering during the pre-start of the container. And that's very important because that allows us to override the attributes that we put by default in the image, either using dependency, because if I use dependency of an image, I can override in the attributes, or I can also override with environment variable during the pre-start. So here is an example. It's using Go templating. And let's say that I want to customize the Redis port in the redis.conf file, and the default will be 6379. And then we have other run levels. I won't tell you all the run levels that we have because we have taken care of lots of use cases, but that one is pretty important. It's pre-start. We have pre-start early and pre-start late. The first one is run before the templating is rendered, and the other one is run after. And we use them to do all sorts of tasks that we want to do to prepare the container before we run the main process. And last but not least, we have testing. Because if you can test, well, it's a bit difficult after that to put that in your continuous integration and so on. So what we do is only batch testing. So I know it's pretty basic, but it works. So what we have, basically, we will have a wait.sh script that will just watch for the container to be ready to be tested, and then the batch file. So here is an example. Let's say that I want to check if Redis server is running in the container and that it's listening on the right port. So to sum up a few Digger commands, we have Digger init to initialize the directory structure that I just presented. So it's easier to develop. Digger try will only do the templating resolution. That's why you can test your templates before building everything, because sometimes the build time is pretty long, and if you've just done a typo in your templates, well, you don't want to run the build each time. The Digger build, do the actual build. The Digger test, well, I don't have to explain. Digger install will put the image in the local in the Rocket local store, and Digger push will push it in a repository. So of course, Digger is on GitHub. You can check it out. And then, well, I spoke about how we're building images, but now how do we run those images? Because at that time, there was no real solution for our scale to run containers in production. So we decided to go with Fleet. Fleet basically is a distributed system that will just launch systemd units on a cluster of servers. So it's really simple, but well, it works. So what we wanted to do with GGN was an abstraction on the top of Fleet to take care of defining the environments and the services that we wanted to run on our production. So here's the directory structure. We have one directory structure for everything that we run in production. We'll define an environment. Here it's prod DC1. Then the attributes relative to that environment. Let's say that I have a specific DNS servers. I have a specific zookeeper for the whole environment. And then the services that we want to run. Let's say that I want to run a Redis quota service, so I will have the attributes, a service manifest, and a unit template. So all of this will be versioned in Git, so the whole team can work on the same base for the launching and defining new services. So just a quick look at what a service manifest looks like. So that's a minimal service manifest. Here I want to launch a pod with a Redis image and a Redis exporter to put metrics in Prometheus, for instance. And I want a 3 nodes cluster. Then I will have the attributes. So let's say here I want to override the max memory of the Redis instance. So from these attributes, GGN will create the environment variables to override the attributes, the default attributes in the Redis image. And then I have the unit template. So the unit template contains the rocket run command with the override attributes and the list of the image that we want to run. In the end, the only command that we have to run will be a GGN prod DC1 for the environment, Redis quota for the service update, and it will just check if the service already exists in the production. If yes, it will check if it needs to be updated, and in that case, it will just take one node at a time and update it and then put it back. Or if it doesn't exist, it will just deploy all the nodes. And the good thing that with GGN, you can also use all the Fleet commands, like to check the journal, for instance, of a specific instance of a service. And then a very key piece of our infrastructure is the service discovery. Because when you have containers that are popping everywhere at a time, you can't just rely on static configuration. You can't rely on DNS, everything. So you need something that can adapt in real time. So what we've done was to start with the Airbnb Smart Stack, which was called Synapse and Nerve. But since then, we've improved it a lot. And we rewrote it in Go. So it's called now Go Synapse and Go Nerve because we have a lot of inspiration in the team for naming. And basically it works like that. So when a service wants to talk to another one, let's say a database, it will have a local HA proxy in the same pod. Then we'll have the Go Synapse, Zookeeper, and Go Nerve each time. So the Go Nerve, which will be in the same pod of the database, will check if the database is okay, if it's up and running, etc. And it will report to a key in Zookeeper. Let's say that the key is called database. In that case, it will report that this particular instance of the service database is up and running. And then in Go Synapse, which is located in the same pod of the first service and the HA proxy, we'll also check the path database in Zookeeper, and it will update the HA proxy directly. So in that case, if there is any change that, on the database size, or if the nerve can't reach the zookeeper or anything happen, well, the database node 1 will disappear from zookeeper, and then the Go synapse will be notified, will update the HA proxy, and node 1 will not be used anymore by the other services. So that's really our Chaos Monkey proof system. Or if anything's happened, everything the HA proxy or in the whole infrastructure are updated directly, and it continues to work. So to sum up a bit all of this, we'll have the bare metal servers. So, like I said, we have only one type of server. Sometimes we have different profiles for the disks, but we try to limit that. Then we have the abstractions with CoreOS and Fleet, which runs everywhere. And on the top of that, we use GGN to run Rocket pods. And in those pods, which are built, it contains images which are built with Digger. And well, here, for instance, 2 different pods with all the images that run in the same context. And they communicate using the service discovery. So Nerve on one side for the monitoring part, and Synapse to update the HA proxy on the other part. Well, this part is pretty much really work in progress, even if it seems that we solved a lot of problems here. We try to stick always to the principles that lead the transformation of this infrastructure. Now we exploit what we can do in terms of orchestration and everything, because well, you can think that it's pretty basic to use Fleet and not a real orchestrator, but it's only very recent that things are going very stable for orchestrator. So we don't want to rush too fast. We have something that works, that's stable. Our main focus now is more to open all this platform directly to the developers, so they can run their own services without asking someone from system engineering. We want them to be completely autonomous, to start their services, to monitor their services, and then we want the system engineers to be only here to create the tooling, improve the tooling, and help the developers when they have a problem, but not doing all the job of taking care of the platform. So that's a big shift. It has also its challenges, like how do you have devs on call, and or how do you decide if a team is ready to deal with a part of the production or not? So I think that we can go for the questions. I wanted to have some time for the questions you could have. You can also ask questions in French, sorry. Yeah.
Thanks for the really insightful talk. I have a few questions. How are you feeling about using Fleet since it has been deprecated officially by CoreOS for 2 months now?
Well, it has been deprecated, but for about 2 months, but it wasn't updated for, I'd say, like at least 1 year. But well, the things works, and even if it doesn't get any updates, well, we still have time. I think we have a lot of time to find another solution and to migrate without rushing to something that would be as stable as what we have right now.
Okay, thanks. Another one. Why did you create Go Nerve on Go Synapse, since it's essentially doing exactly the same thing as console and console templates does?
Well, I'm not sure that it was doing exactly the same thing at the time that when we created GoNerve and GoSynapse. And here I only presented very high-level stuff that we do with GoNerve and GoSynapse, but it's also taking care of lots of small things like our databases couldn't run in production in containers without all the specific features that we've developed in GoNerve and GoSynapse to gracefully put them in productions with warming up with taking care of the warm up and gracefully take them out of productions. All the stuff that we've developed in those tools do not exist in most of the service discovery solutions that exist.
Thanks. Can I ask one more? And thanks for introducing my next question. Since you're running 100% on containers, what databases are you running and how are you handling storing data?
Sorry?
How are you on what databases are you using and how are you storing your data since you're 100% on containers?
Well, all the data is stored locally on each server. We don't use NAS or SAN or whatever. We store things locally. And the databases that we have are very, we have one for each usage. So let's say for transactional, we have MySQL. For distributed, we have Cassandra. We have Couchbase for storing the sessions, Redis for ephemeral, Elasticsearch for search, Postgres for the geo. I'm not sure I have all of them, but you have the idea.
So you were talking about using EPC specification for Digger.
Yeah.
I'm sure you're informed that the OCI from Linux Foundation is now the future for Rocket. So have you studied for the shift? And will it be complicated or will you still use EPC even if it's necessary? Rocket will do the transformation from EPC to OCI.
Yeah, when we saw that the OCI would be the next container image format, we are really wanted to switch very quickly on that. But when we realized that it wasn't going to be stable for at least another 6 months, and I think the stable version will not happen before next year or something like that. So we decided to delay that because it's not a very simple change in the code of Digger or in the code of Rocket. So we're just watching how things are going with that, and sure, that will be the format that we'll be using in the future, but not before a stable version is released.
Thanks for the talk. I'm not sure I got your point about the storage. So you are storing locally all the data. So what happens if you lose a node?
Well, the resiliency is done at the service level and not at the storage level, meaning that, for instance, for our MySQL database, we're using a synchronous replication with Galera. And if we lose one node, when we reboot it somewhere else, it will fetch its data from the other nodes.
So how about the persistent data? I mean, something hosted on the server that need to be used as it is by another node. I mean, like distributed systems or distributed storage.
Well, we have a few examples where we need to have a distributed storage, but that's very few use cases. We have only one or two like that. On all the other cases, we use the replication offered by the application itself and not replication on the storage level.
Right. Another question about when you talk about the snowflakes. So you moved from, can say, pads to cattles. And did you went through re-engineering all the applications, or it was? I mean, how did you manage it?
How did you manage
from the application point of view?
From the application point of view, well, The most difficult thing was not the application, I think, on that part, because we have other challenges that we're having with the application, and they are more in terms of decoupling everything in terms of service and all of this. But even with our old monolith, we can do that. We can remove the snowflakes, because if we lose, for instance, a front server, well, we have the other servers to take care of the traffic. I think that when I was talking about the snowflakes, the real technology that helped us removing those snowflakes was the service discovery, because at that point we didn't need anymore fixed IPs on a few servers that will that will serve traffic from one type of service. We could, if needed, we could add more front servers or remove the one we didn't want anymore, and all the infrastructure would adapt from that.
And the application itself, is it hosted on one server or replicated over, can say, more servers?
Sorry?
The application itself, is it hosted on one server, or is it?
No, it's always on several
okay,
servers in different
spread
tracks and all of
servers.
this. That's something I didn't presented, but for instance, GGN, we can put some constraints to say that we don't want the applications running on the same servers for the same service, or we want to spread among racks, etc. We can put basic constraints. It's not as advanced as things that you could have in solutions like Kubernetes and everything, but we have those basic constraints.
The last question, are you considering Docker for the redesign, or just sticking to Rocket?
Sorry?
Are you considering Docker, or you are sticking to Rocket?
Have we considered Rocket, or are we considering Rocket?
Are you considering?
No. No, we're not, because we've invested a lot on Rocket. We're pretty happy with it, because it's stable for us. So I don't see any reason for using another runtime, at least for production. Maybe that with things we get a bit more flexible for development part, and use Docker for the development part, and then transfer the image to run them on our production servers. But we won't use Docker in production. We had too many bad feedbacks about that.
Thank you very much.
Dernière question, je crois.
So one more. You add a step of hardware uniformization before going on containers. So afterwards, now that you've got containers, do you still think this uniformization is needed? Since, well, containers and orchestration essentially abstract your hardware, so you don't really need to have the same thing for everything?
Well, the thing in hardware uniformization is that it really helps us with dealing with data center operations. Meaning that I just give a sheet of paper with how things have to be cabled and everything to our contractor, and it gets racked and everything like I wanted it to be. So I don't have to go to the data center, and so I have. On one side, it's cheaper than the cloud. Well, maybe I could get some. Sometimes you can negotiate the prices to get to the cloud a bit cheaper. But last time we checked, it was cheaper than the cloud. Now we could switch from cloud to on-prem to whatever. Well, it doesn't matter, because we have the containers, because we have made all these adaptations to be independent from the hardware. So the idea is, of course, yes, we could have different servers and everything, but I don't see the point.
Thanks.
Thank you.